Let's solve the rational inequality here, and we're going to give our solution in interval notation. All right, so let's talk about this just a little bit. We are trying to solve this inequality, right? So we're trying to find x values for which this value here is larger or equal to this value here. The easiest way I think to consider this is probably graphically. We can maybe talk about the graph a little bit. We sort of know what this one looks like, right? If we talk about transformations, excuse me, the graph of y equal 4 over x minus 3, we can draw a real rough sketch of it. It's going to be that guy that looks like this, but we're going to multiply all the y values by a factor of 4 and move it to the right 3 units. So we go 1, 2, 3, So really, really rough sketch. Looks like this, right? Okay, and then this one here looks like this, right? The identity function. So what this original inequality is asking is, where is this figure? So that's the blue one, y equal 4 over x minus 3. We're asking, where is the blue one above or equal to the red one? So this is y equal x. So this is a bit more complicated than we want to think of graphically, which I guess would inspire us to mess with this a little bit algebraically before we even start, because it'll end up being a little bit easier for us. So if we can rearrange our terms where this one's on the other side, that's going to make our lives a whole lot easier. So let's rearrange. All right, so this one's going to go over the other side. So we got 4 over x minus 3 minus x greater or equal to 0 now. Okay, well, we want to simplify this, so we just do, what we usually do. We need common denominators, so we're going to multiply this guy by x minus 3 over x minus 3. And then we're going to combine our terms here, so we got 4 minus x times x minus 3 all over x minus 3 greater or equal to 0. All right, now we're just playing the, playing the simplification game. So we've got 4 minus, then we're going to distribute in here. Maybe I'll rewrite that. So we're distributing. Don't forget to distribute your negative. That's a pretty big source of an error there. So make sure we're distributing a negative x and not just x. Excuse me. So we've got minus x times x is minus x squared. Minus x times minus 3 is plus 3x over x minus 3. All right, greater or equal to 0. And why don't we go a couple steps further here, rearranging and make our lives easier in the end. So we can take a negative out of all these terms. So what we want to write this as is a quadratic on the top, right? And in the regular form that works for us, we want to have a positive coefficient on the x squared term. So we can factor out a negative and just rearrange the terms. So we're going to put this one first. So if I factored a negative out of there, it's positive now. And then I'm going to have this term. If I factored a negative, that's going to be negative now. And if I factored a negative out of this one, that's also going to be negative. So now we got this in this nice form that we're used to. And we can, x minus 3, excuse me, greater or equal to 0. Okay, so we're almost done setting ourselves up for success here. One last thing we can do is we could factor this, and we can multiply both sides by a negative. So if we multiply both sides by that negative, maybe I'll rewrite this with a, we can multiply both sides by a negative, well, maybe negative 1. Okay, this is going to switch, right? That's another critical error that we sometimes make. We multiply both sides by a negative and we'll forget to switch that sign. So we're going to switch it right now so we don't forget. 0 times negative 1 is again still 0. And then we can just factor this guy. So we've got two things that multiply to be negative 4, add to be negative 3. We're going to have x minus 4 and x plus 1 over x minus 3. Okay, so now we have transformed our original inequality that we had to, I would argue, be a bit simpler for us to look at. So now, if we're looking at this graphically, we can remember what this looks like graphically, right? The zeros of the numerator are going to be our x-intercepts, and the zeros of the denominator are either going to be holes in the graph or they're going to be vertical asymptotes. So we can draw a really rough sketch of this as well. This is all separate here. So we're thinking about the graphs over here. So this graph, this one, we would have zeros here and here. So if we were just drawing a really rough sketch of that, we'd have 1, 2, 3, 4, boop. And then this one would be at -1, boop. And then we would have a vertical asymptote at 3. So what this graph would look like, well, these are pieces of the graph, right? Here's a vertical asymptote, here's x-intercepts. So the interesting thing about this, or I guess maybe not interesting, it might not be the best word, but useful is definitely the right word, is that these points here, the zeros of this, the zeros of the numerator and the zeros of the denominator, these features of the graph, this is the only place where the graph could possibly cross the x-axis. So that's useful for us, right? Because now, you know, let me just draw a sketch here. Maybe it looks like this, maybe it doesn't. We don't exactly care. I mean, we care, but not exactly. So maybe, you know, maybe it looks like this. Who knows? But we're asking, where is now this function above or below the x-axis, right? So we're asking, where does it switch from being negative to positive? Well, here are your only options. So x equal -1, x equal 3, and x equal 4. These are the only x values at which it changes sign, at which it could possibly, I guess. Could possibly change. Well, that's weak. But we fixed it, right? So these here are the only x values at which our rational expression here could change sign. And that's what we're after, right? We want to know where it's below 0. So we're going to go ahead and make ourselves a nice sign diagram. I'll use this different color because that blue one looks like it's kind of running out. So we just want to take and plot these on a number line. So we got -1, we got 3, whoops, and we got 4. You know, they're not evenly spaced, but it doesn't exactly matter. Okay, so we're going to test something in each of these intervals that are kind of separated by these numbers. So we can do that, right? So we've got x equal -1. So if we're testing these in our a rational expression here, all we really care about for the sign diagram is the sign, right? We're really asking, where is it negative or equal to 0? So we really only care about the sign. So let's only write the sign. So if I put -1 in there, this piece right here is going to be negative, right? -1 minus 4 is negative. So we've got a negative there. This one's going to be equal to 0, right? Well, we shouldn't have done that. So if we put in -2, excuse me, we're picking values completely within these intervals, right? So x equal -2, so that's completely within this interval. All right, so we still get a negative if we put it into the first factor in the numerator. This one, we're going to get a negative, right? Negative. And then this one's going to be negative. -2 minus -2 minus 3 would be -5, so that's negative. So all together, we got a negative times a negative, which is positive, divide by a negative, so end result, it's negative. So over here in this region, value is negative. So any x value over here, it's going to give us a negative value for our expression. All right, so we can do another test value here. X equal, probably pick something in here. The easiest thing to pick would be 0. So if we pick 0, we would have a negative, we would have a positive, we would have a negative. So that result would be positive, right? Negative times positive is negative, divide by a negative would make it positive. So everything here is positive. Okay, and then we pick another test value, so we'd probably pick maybe 3.5, and we would check out the sign on that as well. So that would make this piece would be negative, this piece would be positive, this piece would be positive. So we got negative, positive, positive. So that's a negative altogether. And now we pick maybe x equal 5. So we can try putting 5 in there, right? That'd be a positive value. This would be a positive value. 5 minus 3 is also positive, so this gives us a positive. Okay, so this is positive here. Okay, so one last thing that we want to do. So we know that these are the boundaries of the intervals of interest, but we want to decide whether or not we include them. So our inequality is a less than inequality. It's less than or equal, so it's non-strict. It could be equal to 0. So these boundary points that gave us 0, which are exactly the numerator's zeros, these are going to be included because it's equal 0 at those points, right? If I put in x equal -1, we get 0. If we put in x equal 4, we get 0. But if we put in x equal 3, this is undefined, right? So we can't include x equal 3. And if we're looking at the graph or thinking about, I know that the graph probably doesn't look like this, but it's got these features, right? The intercepts, and it looks like based on our sign diagram, it would actually be the opposite behavior here, right? Of what I drew, but you know, the idea is still there. Okay, but the idea here being the asymptote, right? There, it's undefined here, so there are no values on that line x equal 3. Anyway, we're going to take our sign diagram and we're going to finally answer the question. So we were asked to solve this inequality, which was initially up here, and then we rearranged all of our terms to find our zeros of the easier one, right? So we wanted to know where this object is less than or equal to 0. We made our nice sign diagram using our possible zeros of the numerator and the denominator. We excluded 3 because that makes our expression undefined. So now we just have to write which intervals are, well, less than 0. So we include this, and we want the -1, we want the -1. So we're going to say -infinity to -1. We do include -1. So this interval here is all negative. We don't want this because it's positive. We do want this because it's negative. So we do a union, and then 3 to 4, and we include 4. Okay, so now we have our solution set, and we can absolutely check this. I mean, it would be impossible to check all the real numbers in this, but we could certainly take something in these intervals or take something in between these intervals and test it on the original one, right? Because we probably should do that. Maybe we made a mistake somewhere along the line there that we didn't catch. So we ought to check in the original statement when we're finished, or the original inequality rather. Anyway, that's it.